we'll discuss one topic, and that's simple harmonic motion. And we'll see how this is an application of the second order linear homogeneous ODE. So we just start by describing Hooke's law. Now, Hooke's law is what happens when you displace a block that's attached to a spring by a certain amount. So if you pull a block that's attached to a spring by a little bit, notice the string will pull back on it, and the force acting on the block will be in the opposite direction of the spring. Opposite direction of the displacement of the block. Likewise, if you push the block in, notice you'll feel, if you push against the string, what happens? Well, you feel a force that's pushing back against the block, that's the spring force, and it's always in the opposite direction to the direction in which the object is displaced. So that is summarized in what's called Hooke's law. The force F acting on a block is given by F, the force, is negative K times X. X is the displacement of a spring from its equilibrium or resting position. So this first picture here, that is resting position. Second picture here, X is its displacement. It's positive if you pull the object attached to a spring away from its resting or equilibrium position. And this last picture here is what happens if you put the block in. X in this case is negative because you're pushing in instead of pulling away. K is a positive constant that depends only on the spring. Now, recall there's Newton's second law, and Newton's second law gives the equation of motion. What Newton's second law does is it relates the force that acts on an object to its mass, m, and its acceleration, a. It's given by the formula F is equal to ma. If x of t is a position of an object, say a spring at time t, then the acceleration is the second derivative of the position, x double prime of t. If we're on a spring, notice the force is now given by Hooke's law. It's negative k times the displacement. So negative k times the displacement is equal to m times x double prime. We add k times x of t, we get x double prime plus k over m times x of t. So that's just rearranging this equation, dividing through by m. But what do we know about this equation? It's a second order homogeneous linear ODE. Well, that's not too bad to solve. We've seen that before, right? It was actually one of the simpler equations to solve. It's not even non-homogeneous. There's no term on the right-hand side. Now, there would be if we had, say, a damped spring or maybe some force of friction. But in this case, this is simple harmonic motion where there's no friction. The only force that's acting on the spring or the object attached to the spring is the spring force itself. We can solve this using the characteristic polynomial. Replace x with r, replace double prime with square, replace x with r, k. Well, this is really r to the 0 power, r to the 0, or anything to the 0 power is 1, r squared plus k over m. What do we get? We get r squared plus k over m is 0, r squared is negative k over m, r is plus or minus square root of negative k over m, which is plus or minus I times square root of k over m. Set omega is square root of k over m. So we have linearly independent solutions. x1 of t is cosine omega t. x2 of t is sine omega t. X of 0 and x prime of 0 are needed to find x of t. So notice these two values are going to be initial conditions. If we don't have them, x of t is not going to be completely determined, except in special circumstances. And there's an important new form for the general solution. Writing down c1 times cosine omega t plus c2 times sine omega t, it can be kind of annoying because we have two trig functions. Let's set c equal to square root of c1 squared plus c2 squared, and we determine the constant delta from the following. Sine of delta is c1 over square root of c1 squared plus c2 squared. Cosine of delta is c2 over square root of c1 squared plus c2 squared. What's really going on here is if you think about a right triangle, this can always be determined from the right triangle. We have C1 here, we have C2, and then from the Pythagorean theorem, the hypotenuse is going to be C1 squared plus C2 squared. And of course, in that drawing, delta would have been the angle. So I'll try one more time. C1, C2, delta is this angle here, and the hypotenuse has length. Square root of C1 squared plus C2 squared. So this delta over here is this angle between C2 and the hypotenuse. In this case, we can rewrite this. So what's really going on here is if you replace C1, or if you divide through x of t by c, square root of C1 squared plus C2 squared, and also multiply by, so really you're dividing by c and multiplying by c, 1 over C1 squared plus C2 squared times C1 over C1 squared plus C2 squared. This becomes sine of delta times cosine omega t plus cosine delta times sine omega t. That becomes the sum. There's a sum angle formula for sine. It says that's the sum sine omega t plus delta. You can read about that in your textbook. And of course, we have c lying out here. The nice thing about this form for x of t is that there's only one trig function to worry about, just sine. Just keep differentiating sine. That's usually easier to worry about than C1 and C2. And in fact, sometimes it's easier to solve for C and delta than for C1 and C2. And especially in physics, this form is used a lot. Delta is sometimes called the phase. And this, or rather 2 pi over this, is going to be the period. So omega is where you get the period. And you have period and a phase. And that's important for harmonic motion and their applications in physics. So let's start with an example. Let's say we just have, try to keep it simple, spring constant 1, it's at rest or equilibrium. And as we see here, what do we have? We have a 9 kilogram block that's attached to the spring. We displace this block 1 meter from equilibrium. See 1 meter down here. It's 1 meter from equilibrium, and it was originally at the origin, goes 1 meter over, and initially we just displace it, its velocity is 0. Now we could be, say, forcing it, or we could pull it at a certain velocity, but we're just going to pull it back and then just let it go. That means when we just let go, the initial velocity is 0. If instead we were, say, pulling it back and then also pushing it, say, we could have also given a velocity that was, say, pushed backwards, where the block is going to go because the spring is displaced in the positive direction, then that is going to change the equation of motion, and that's also, or it's going to change the initial conditions. It's not going to change the equation of motion, but it is going to change the initial conditions. So this, the displacement of 1 meter, and the initial velocity of 0, these are 2 initial conditions. Here's what we get for equation of motion. Omega squared is k over n, which is 1/9. 9 kilogram block, k is 1. Omega is 1 over 9 square rooted, so it becomes 1/3. Square root of 9 is 3. Equation of motion is x double prime plus 1/9 x of t, and it's 0. So what are the initial conditions? We just saw above, it's x of 0 and x prime of 0 is 0. x of 0 is 1, right? Its initial displacement was 1 meter. Its initial velocity was 0 meters per second. What's the general solution? Constant times sine omega t plus delta. Now just replace omega with 1/3. So this omega here became 1/3, and we get c times sine 1/3 t plus delta. Now we're going to plug in t equal to 0. What do we get? We get c times sine of delta is equal to 1. When you differentiate this, right, this is the chain rule. Derivative of sine, the outside function is cosine, multiplied by the derivative of the inside function. That's the derivative of 1/3 t plus delta, which is 1/3 times c times cosine 1/3 t plus delta. So we get x prime of 0 is c over 3 times delta of cosine of delta. C sine of delta is 1. C over 3 cosine of delta is 0. C sine of delta is 1. C cosine delta is 0 because multiplying that c over 3 cosine delta by 3, well, multiply the right-hand side is 0. Multiplying 0 by any number is going to give you 0. Square both sides, and we add c squared cosine squared delta plus c squared sine squared delta, factor out of c. What we're left with is this. So why do we do this? We did this because cosine squared plus sine squared is 1. And that's a way of eliminating sine of delta and cosine delta. So that's actually a common trick. Try to get the equation lined up so it looks like constant times sine, same constant times cosine, square both sides, and then solve for c squared. That's a way of eliminating delta in this case. Remember, cosine squared plus sine squared is 1, so we get c squared is 1. Remember, c is positive, so the only solution is going to be 1. The solution is technically the c squared being 1 or plus or minus 1, but because c is positive, we just get positive 1. Sine of delta is 1, cosine of delta is 0. What does that mean? That means delta is pi over 2. So what's our solution? C is 1. 1 times sine of t over 3 plus pi over 2. Voila. Okay, this is a pretty straightforward function to deal with. We can plug this in. We can look at what it looks like on a calculator. And I will actually be uploading a video as to what the motion of the block on the spring will look like. It oscillates between a position of -1 and a position of +1. -1 being the position obtained when the block is pushed in by 1 meter of the spring, and maximum displacement of +1 when the block is pulled out. So notice initially it was pulled out and its initial displacement was 1. Notice here, of course, what's happening when you push back against the spring pushes back against you. That's actually Newton's first law. And, I'm sorry, that's Newton's third law. For every action, there's an equal and opposite reaction. When you pull out, when you displace the spring, right? Now the spring force is acting the other way. It's pulling back, the block back, and that's why it oscillated back towards equilibrium and then eventually towards -1. It keeps oscillating. So there we see minimum displacement, -1, because -1 is the smallest number x can be. And of course, the maximum displacement of +1. That's the largest number that x can be. Okay, so don't forget to look at the video. That's a good visualization. We do have some web assigned problems about this. In that case, sometimes f is unknown, sometimes m is unknown. You might have to solve for those quantities before solving the ODE, but the ODE in simple harmonic motion always has the same thing. X double prime plus omega squared x is equal to 0. Sometimes there might be a term on the right-hand side that is damping or obtained from another force.